Hello everyone, my name is Chad Germany, and yes, backed by popular demand, I'll be presenting another experiment for our 1B class. This experiment stemmed from the puzzle that Leonardo posted on NiceNet, which basically asked the question whether a fisherman, after he drinks a can of beer, whether the water level increases or decreases or remains the same when the can goes to ocean floor, opposed to it being inside the boat. So I did the experiment, and let's do it right now. Let's do it right now, okay? And everyone remember this. This is a very important fact. An experiment is worth 1,000 expert opinions. Just remember that. Alright. Can you see me now? Can you see me now? Can you see me now? Good. Alright. Some Lincoln Park. Alright. Right now the little boat, or whatever you want to call it, is floating, and the buoyancy force is equal to the weight of the container. So what I'm going to do right now, I'm going to put a bunch of these beads, or whatever, for decoration. I don't know what they are, but I'm just going to put a little bit of them, or just pour them all in. Okay, make sure that they don't fall into the water. Okay. Alright. Now I measured the dimensions of this container. Well, no, I just measured the area, because that's all you need. I measured the area of this, and this is like 9 by 9 centimeters. So translates to 81 centimeters cubed, or centimeters squared. And then it goes down by inch, or a centimeter. So you then times that by 81 centimeters squared and get 81 centimeters cubed. And that's basically the volume of the row. The volume of the row G V. So that's the volume right there. Can you see it? Oh, there it is, right there. That's the volume, and I just measured that. And that's important because that's how much is sunk down is delta B, and what that is, that's the weight of all these beads that added to it. So the beads made this thing go down because it's additional mass. Alright. And what Crown eloquently put inside his response to the puzzle was he stated that since the beads are inside the container has a huge volume. But as you put them out, you dump all these little beads out, they have their own little volumes. And whenever you increase or decrease a volume, then you decrease the density. Or you increase the density. You decrease the volume, you increase the density. So these densities increase. Thus decrease, if you decrease the volume, then you also decrease the buoyancy force. So let's take a look at this tape. The tape is like right here. I don't know if you can see it. Yeah, it's like right there. See it? Right there. Okay. That's how much it changed. So now I'm gonna dump all the water out. Let's see. I mean all the beads out. And we're gonna see how that's gonna affect it. Oh, what's going on? What do we have here? What is this? This is crazy. This is crazy. Look at this. It actually went down from the mark by a measurable margin. It's like half a centimeter, maybe. Yeah, it's about half a centimeter. This is amazing. Well, we know that when it's dumped inside, it has a lower volume. The individual ones have a lower volume than the one on top because push this down, this container, it floats because it has a very high volume compared to its weight. But if you dump all these little things inside, then their volume is very small, so they're very dense and thus take up a low volume, low area or volume of space in the water, and thus sink. And on the bottom floor, there's also one more force that's keeping these things from falling through the table and falling through everything, and that's normal force, which is caused by, you know, electrons repelling each other. We're never really in contact with our material. It's just the little valence electrons kind of repelling each other. Electrical forces. But that's 1C. Alright. So you all see this. This is quite amazing, I think. Non-intuitive. And it doesn't matter if it's a can or if it's a bottle or anything. Since it's filled up with water, the only density or weight, the only thing you're looking at is the actual material, the volume of the material that goes inside, because you don't pay attention to the volume inside since it's going to be filled up with water. So you can imagine you're balling a can up to like a size like that, and then it sinks down. So it doesn't really matter. If you want to find the volume of the can, you have to times its thickness times the surface area. Then you'll find the volume. But that's it. Oh, you want to see the picture? See? Density. This is change in everything. And look at coordinate system. Don't forget that. Alright, I guess that's it. If I'm not missing anything, right? That's quite startling. I think that's pretty amazing. Oh, look at my wall. Can you see it? It's just basically equations all over it. Alright. And that's why I went the chalk, Mr. L. Right, equations all over my room. Alright. That's it. Peace.